gamma is finite. So it belongs to the, it is definitely non-negative. Then gamma is called the rectifiable curve. I don't know why mathematicians use this word.
There's one more question.
Yes.
X should be some. There should be some order on X. Otherwise, how we will define
Yes.
prima?
Order.
No, order on the X. Otherwise, how we will define a prima?
No, this supremum is our real number, so no problem. This sum is a real number. Yes.
Thank you.
S may not have anything.
Yeah. Sorry.
So this is definitely a non-trivial concept, right? Non-trivial. It's you should really try to have it as your own. I was struggling because definitely you have to have gamma in. Let me rewrite it. Correct my mistake. And then this graph is no longer needed now. So we're looking at the distances, some of the distances of gamma x0, x1, x0 and gamma x1. Some of the distances of gamma x1, gamma x2. Some all the way down to n long. And then x 0. This sum is the sum of non-negative real numbers, which may not be bounded above. If it is bounded above by completeness axiom of the real numbers, this supremum exists. If it is not bounded above, then this one is undefined. It's L gamma. If it is defined, then we call it rectifiable. Should naturally follow, but didn't follow from this observation. But I forgot what was next. I also forgot what was next one. So this is called the rectifiable curve or path. Now, the definition of a geodesic, which we have been using all the time. The definition of a geodesic is the distance between if L gamma, the length of a gamma, of this gamma, is equal to the distance between rho gamma 0 and gamma 1. Of course, this one is equal to 1. This one is equal to 0. You could add. The x0 is 0 and xn is 1. If the length of the gamma is equal to the distance between its initial point and the terminal point, then gamma is called the geodesic. This is the definition of a geodesic. We didn't use any differential geometry. Then gamma is called the geodesic. Geodesic in a matrix space. You have to really know that you have done lots of nice courses, especially from those European colleagues. In differential geometry, you have to introduce a Riemann metric, which assumes completely smooth, infinitely differential. And then you start to define geodesic using Euler-Lagrange equation, right? In variation of calculus. Now here we don't have any differentiability, or we only have some continuity condition. Continuity condition gamma is satisfied. We don't have any differentiable things, differentiability condition in order to define geodesic in a metric space. You need to really know that this is far below the differential geometry, which means the differential geometry man 1 must be able to be deduced from this as well. Differential geometry geodesic.
In differential geometry, you intuitively say that geodesic is the shortest path.
Yes.
It would it the same case here as well?
This is the same. Yes, but there the shortest thing is done through what? Through variational calculus, using Euler-Lagrange condition. So there, strictly assuming everything is differentiable. Here, nothing. No differentiability here, except continuity. So you need to know that this is far below. I'm saying this is easy and basic course, meaning that we are not even as high as basic differential geometry yet. So this is the advantage of this course. Only metric properties are concerned. So now it comes to the famous things which were stated many times in history. So if you have a geodesic, if gamma is a geodesic and take any 2 points x, y on it, then the section between x and y is the shortest of the paths connecting x and y. This can be said now. So we will write it down. If gamma is a geodesic, and x, y are on gamma, meaning that it is in x, but it is image of some points in 0, 1, 2, on gamma, and they are not equal. Of course, if they are equal, the first axiom said the distance is 0 and definitely shortest among anything containing a point to itself. Then the segment means that it is gamma x, part of gamma from gamma x and gamma y is the shortest among all paths. If it is a geodesic. Now, everything else I think I can recall, especially this. If X is a metric space, such that for every x, y, in x, there is a geodesic connecting x and y in x. Geodesic was earliest understanding of geodesic was definitely in differential geometry. Unless if you believe Euclid or Hilbert saying that shortest distance between any 2 points in a Euclidean space is a straight line segment. That was one of the things which led to Hilbert's fourth problem. But nowadays, I don't want to talk about it because it's too big. That problem is too big. Many mathematicians think that it is ambiguous because it was solved and it was still unsolved. Hilbert's fourth problem was answered. Some people, 2 or 3 people, famous people, thought the answer. And then as soon as one answer comes out, it becomes, again, not solved. So it's a very interesting history. You should check out online. They're all online. So if between every 2 points there is a geodesic connecting, then we call the space self-geodesic space. X is called the geodesic space. Now, I want you to tell me quickly what geodesic spaces examples, what examples of geodesic spaces are there? You know, right? Real line and actually any Euclidean space. Good. So example, Rn or any natural number is geodesic. We believe Euclid's shortest distance between any 2 points in the Euclidean space is a straight line segment, and that is the geodesic, no problem. Right. And that axiom was questioned by the Hilbert's fourth problem. Anything else?
Sphere as well.
Sphere, yes. So we add we add Riemann spaces. You need to verify that, or not only by saying, but any dimension.
Yes.
Anything else? Hyperbolic spaces. It has a special symbol reserved for it as well. Hyperbolic spaces of any dimension. These are all actually from differential geometry. But in differential geometry, there is a nice definition of what is more called curvature. The curvature of this is zero at every point. And curvature of this is assumed to be positive at every point, same positive constant. And usually you can actually assume that it's 1. And curvature of this at every point is -1. That was, and these three types of spaces are called geometric spaces. Anything else you can think about? Maybe not. I'll add one more, which is just pulling out from the air and adding in Riemann surfaces. We're going to define this vigorously in the fourth batch of slides. We are currently towards the end of second batch of slides. Riemann surfaces are essentially precisely defined to be solution of a polynomial equation of two complex variables. Just one polynomial, f is a polynomial with constant, the complex coefficient. F, W, X, Z is a solution of that. Any solution of any one of these polynomial equations is called Riemann surface. I think it's probably in algebraic geometry. Nowadays they use this definition. Of course, there are equivalence definitions like it is the domain of definition of holomorphic functions, one definition. Another definition says that it is the image of a holomorphic function. There are others as well. But why is this a polynomial definition using a polynomial of two complex variables advantageous? Because it immediately puts it into the category of algebraic variety on one hand. On the second hand is symmetric. You can actually, you don't have to say image or domain. Thirdly, it is easier to work with. So if there are three good advantages, three good reasons for using a concept instead of an equivalent, another one, then you use this. Oh, yes, there's an important example. We have we have seen at least three different distance functions in any Euclidean space. let us just consider Euclidean plane. Of course, it works for any dimension. Euclidean plane with rho 1 distance. What was rho 1 again?
Distance.
Many people call it Manhattan distance. I don't like that kind of vulgar word. Rho 1 is sum of the absolute value, sum of the distance, absolute values of differences in each component. That is where the exponent on each of the absolute values is 1. That is why it's 1. And rho 2 is the Euclidean distance. R squared rho 2. This works for every n. Rho 2 is the Euclidean distance, which is given by square root of sums of the squares of distance and differences. The square root x1 minus x2.
Distance formula.
Huh?
Distance formula. Here in the second one, you can say that it's a distance formula in Euclidean system.
Yeah, the Pythagorean distance formula.
Yes.
This is also a distance formula. Because it's a distance. Both these are geodesic. Both these are geodesic. This one is geodesic, depends on the Euclidean statement that straight line segment is the shortest. That is an interpretation of that statement. How about that one? Between every point, every 2 points, x, y, until you get to this one.
Yes,
These are all distances. So these are all geodesics.
shortest paths, yeah.
Yeah, geodesics according to our definition. This means that in that, and you know that that is also intrinsic distance here. There are two intrinsic distances of this. Intrinsic means that the distance is given by geodesics by our definition, I think. Yes. Where is the intrinsic? Hmm? Intrinsic is not defined yet. Oh, sorry. Defined it here. I forgot because it's in this. Gamma is a path and rho xy is equal to L of gamma x. Let us say path conjugate xy be any two values. Gamma is the path connecting x and y. And rho xy is equal to length of gamma. The length of a geodesic gives exactly the distance. Then we call this distance, this distance function intrinsic. This word we have been using many times. Now, even in this one, distance between x and y is given by the length of a geodesic connecting them. Of course, there are infinitely many geodesics. And in this one also, distance between any 2 points is given by a geodesic, length of a geodesic connecting them. Which means both these two distances, which are different metrically, are intrinsic distances. This also shows that intrinsic distance of a metric space is not unique. So this is a good example. Function, if any, if it exists, may not be unique. These two distances are different. Of course, topologically, they give you homomorphic topological spaces.
Is there any condition on gamma? Because if we choose arbitrarily a different gamma, then length of gamma could be different one.
Gamma is the geodesic. Shortest path.
Yeah, then it's
The geodesic. If there is no geodesic, we use shortest path. Thank you for correcting. This is vital. This is one observation, and this example is important. There's another observation which leads to lots of interesting research. Actually, now, although it is very basic, we're now coming to some research questions as well. Let us consider the Riemann space of dimension 2, which is the space. So let us consider the unit space. Unit sphere has a pair of points where there are infinitely many geodesics connecting. Which pair of points? The unit sphere has a pair of points where they are connected by infinitely many geodesics.
opposite pole.
Yes, end point of any diameter. So let us, I have got some nice drawings in the computer, but let us, my hand drawing is extremely bad. Let us assume that this is a circle. You have to assume, otherwise it is not. That is another circle which you can probably imagine that it's the equator. So you have any point here, and there is a center of this unit sphere has a center which is the origin. So if you draw the unique straight line connecting these 2 points by Euclidean axiom, it will intersect the surface into another unit point. And those 2 points are endpoints of diameter. At least they are connected by 2 geodesics in its intrinsic distance. Of course, the Euclidean distance is 2 of those 2 points, but the intrinsic distance is pi. And there are infinitely many, because you can also have another one going this way. And not only so, this space has a property that there exist 2 points. There exist points x, y, a, b, such that the whole space is equal to the union of geodesics connecting a unit. If you have these 2 endpoints of any diameter, then take all the geodesics connecting these 2 points, which is essentially the semicircles rotated 2 pi, which sweeps through every point of the S. So any point, proof is very simple. Any point in this is on a unique, somehow unique geodesic line, or unique geodesic, or another unit geodesic connecting these 2, except that point is this one, and you might. So this space has this property that. Now let me ask you a question. This question you should do as an exercise. Which matrix spaces have this property. Characterize all metric spaces such that it has the property that there exists AB such that X is equal to union gamma connects AB. Gamma is a geodesic connects AB. This is the question. Someone should be saying that I will be able to solve it by tomorrow.
I don't know the proof, but I know the answer, I think. Once we once
Please try to prove. You might be probably looking at the field here if you're not 30 years old. It's not an exercise question, definitely. I don't know the answer yet.
maybe that was the partial answer.
Yeah, is your answer to include those which have a sausage-like thing in it? The right circular ellipsoid, finitely many of them join at the extreme points. Whichever way they go, it doesn't matter, but that satisfies this condition. Yes. Let me draw a sketch. Suppose that you have this right circular ellipses. Right circular ellipses mean that if this is the axis, then this is obtained by rotating. So that there, this is a circle. This has to be a circle, and that doesn't matter. And you join it to another right circular ellipse, and you can even introduce line segments and join. This satisfies this condition. I know, but I don't know if some metric space satisfies this condition. It can be only such. I don't think so. I have infinite examples which are not these this way. For example, let me give you another one. This everybody knows from discrete mathematics. A has 3 elements. So this is A. Here we have AB. Here we have AC. Here we have BC. These are contained. And there we have A. Here we have B. Here we have C. A is contained in these two. B is contained in those two. C is contained in these two. And we have empty set. All subsets are set with 3 elements. Of course, you know that this is a unit cube.
Yes.
This satisfies this condition. Although the geodesic now becomes shortest path. For example, you have this point and that point. Every point is on the shortest path connecting those two. This is definitely one of these. Of course, you can replace each of these by right circular ellipsoid. No problem. Same thing will hold. It is this kind of research I would like to be doing since 2012 and did publish several papers on this. So if you replace some of these, any subset of these edges, is the graph, of course, by right circular ellipse, or even paths of the same length at every level. Same thing holds. But I don't know the answer of this question. So if you are, let me tell you a story. In South Africa, she died now. She's we call her South African, mother of South African graph theory. All her life she did graph theory. She was attending, when she was a master's student, she was doing it in United States, attending a graph theory lecture by Peter Slater, famous. And Peter Slater wrote something on the board on this. Her name is Henna Swart, white lady. She came late, and then she copied the question, and she thought it was an assignment. So he worked something like a whole week and then proved one of them. And then brought it to his assignment and brought to Peter Slater. And Slater was immediately stricken by this. It's a new theory. That's how she did her PhD. She was thinking it was an exercise question and then did it with some labor. And then she got a PhD because of that. And she's extremely clever, by the way. She died 10 years ago. Unfortunately, because she was our mother in South Africa. Now, not only this, there are lots of other questions concerning geodesic existence of some points, so that geodesics connecting them satisfy certain properties presented using distance only. This is.
Do we know any partial answer to this question? Like there is a class of symmetric spaces which
That,
satisfy.
we characterized actually. We characterized graphs which are of this problem. And this paper is published already. This paper is published last year. Well, I did it in 2018 in Auburn University, but the final publication, because we never submitted. We submitted and it was accepted immediately in this case. There was only one error. Let me tell you, it's very funny. This submission and the paper rejection acceptance is very interesting. The referees, two referees, pointed out that AMS, I was using 2010 classification. He said, it might be he. The two referees both said this one should be changed to 2. That was the only correction. You can see that how you feel. I felt very happy. There was an error. So funny, isn't it? Some referees are really humorous because it doesn't matter which year it is actually, but there is an error there.
Did they call it major error?
Huh?
Did they call it major revision or just minor?
Yeah, this is
Yeah, definitely this is minor, but what did they call?
it's minor, of course. There's one place we suggest you change that 1 into 2, and then I did. Very funny, isn't it? So this is one. There are lots of other questions here. We are going to state that later. Now,